Welcome back. It's my pleasure to introduce our next speaker, Martin Takac. Hi, Martin. Martin is an associate professor and the deputy department chair of the machine learning department at Mohamed bin Zayed University of Artificial Intelligence in the UAE. Before that, he was a professor in our department here at Lehigh in the ISE department, and we were extremely sad to lose him, but it seems like he's doing amazing things in the UAE, so we're happy for him. He got his Ph.D. in math from the University of Edinburgh, and he does a lot of research on algorithms and applications for machine learning in all sorts of different arenas. Martin is also going to be joined by Ruben Solozabal, who is a postdoc now at the same university where Martin is in the UAE. He has his PhD in applied machine learning from the University of the Basque Country, and his research interests include reinforcement learning for combinatorial optimization, deep learning, telecom, and quantum chemistry. Thanks, guys.
Hi, hope you can hear me. So thank you, Larry, for a nice introduction. And I will be speaking about joint work with many great people. Of course, Larry and Afshin and Mohamed and Zayed and Taoli. So those are the guys which I collaborated at Lehigh. Now basically moving here to UAE, I was still working with Taoli a little bit. I also have some student Shahad and of course Ruben. Over the last few years, I was using the higher level programming languages called postdocs and students. So basically therefore somehow use this opportunity of this virtual talk to also welcome Ruben. You can say hello. So I'll try to speak more about the experiments and basically the things what he was doing there. Okay, so let me start. So I will speak about two different applications: stochastic VRP, vehicle routing problem, and also stochastic job shop problem. And basically, what is it? I'm pretty sure that everyone knows. Just very quickly recap. When I have some depot, I can have many cars. And many times I have multiple demands from customers. So basically in this case, I got some graph because I'm trying to use some edges to deliver some products. And because I have some capacity on a car, I cannot have one car just to visit every single node, basically TSP. But I can someone decide to send multiple cars to different customers, then go back to depot to refill the car, send one more time different route, again, I can repeat this one many times. I can use multiple cars. There are clear challenges because many times, even the travel times are not exact, they are stochastic. Also, the cost can be stochastic because again, the travel times can change, also the cost can change. Also, we have a stochastic demand. So basically many times we don't exactly know how much the customer will need. Maybe we just learn in the morning. Or basically we can try to estimate what can happen. Okay, so there are many challenges with this approach, which is something to address. We can also think about the job shop problem. In this case, you can have few jobs. Every job has multiple tasks, which can be completed on different machines. We can be given multiple jobs, which is a sequence of tasks, and we know maybe the time, how long does it take, and basically what is the order of machines. This should be somehow processed. So in this case, if you have job number 3, should basically first be processed on machine number 3, then machine number 4, then machine number 6, and so on and so on. Okay. And also here we can have many challenges. Maybe the processing time, basically in this case, like from maybe 10 o'clock to maybe from 10 to maybe 18. Also, this can be somehow stochastic, and many times there could be some features which can influence these times. Also, you can think about maybe there could be some additional time needed to adjust one machine from one task to different tasks. Okay, or basically from having one machine to be used for job, let's say 3, then maybe to job 6. So there are many different formulations you can think about, okay? So I'm trying to say that if we can use different approach than just the classical modeling which we use in optimization. Okay, there's one challenge I also wanted to discuss, that we can have demand or processing times which are somehow stochastic. But also those could be somehow correlated. Think about this one, when I have some snowstorm, clearly, if there is some snow in, let's say, Pennsylvania, so in Bethlehem city, then there will be also some delays in Allentown and surrounding area, okay? So many times, all those times can be correlated. And also, let's say, demand, when you have, say, demand for ice cream, of course, there'll be also some additional hidden features, let's say, maybe the weather, or maybe some kind of like wind speed, or maybe rainfall. They all will influence both the travel times, let's say, the demand, and all those different things, okay? So there is natural questions. If I have some features, some external features, how should I approach this problem? How should I formulate this VRP, or maybe some formulate this like job shop and so on, okay? So classically what we can do, we can take this historical data, we have some huge database, we have the features, let's say temperature, wind speed, and so on. We can also have some historical data for demands for different customers or different nodes in the network. For example, for VRP, I can also have some historical data about travel times. Maybe I can have, let's say, January 1st, there was delays almost on every highway. I can really have all this historical data. I can also have maybe some historical data about processing times for job shop and so on. So what I can do with this, I can maybe make some assumption. Maybe I will assume maybe the demand will be normally distributed with some mean and variance, okay? So basically we'll assume that there will be something, some laws about the demand, the processing times and so on, or travel times. What I can do afterwards, I can try to build some predictive model, okay? I can be maybe making some linear model, maybe not sufficient. I can maybe use some kind of like machine learning, like deep learning model to predict maybe the mean and the variance or the standard deviation. Most likely, I will also make assumptions that my, let's say, random variables will be uncorrelated, okay? So they'll be independent from each other, okay? After I build the model, let's say the next day morning, I can observe the features. I know there is no rain, maybe 50 degrees Fahrenheit like this now at Lehigh. And basically afterwards, I can use this predictive model to maybe estimate the mean and standard deviation. Once I have this mean and standard deviation, I can maybe just sample many different scenarios. I can formulate some kind of like optimization problem. I can maybe like use mixed integer problem, and doesn't matter what I use as a formulation. Maybe afterwards I can try to use either Gurobic, Cplex, any different solver I want to use to maybe obtain some solution. Let's say for VRP, I can obtain some kind of like decisions, let's say how to route my cars. For basically job shop, I can obtain this scheduling of jobs on the machines, and basically I'm done, okay? Clearly, there are some strong assumptions which we made. We assume something about the distribution of the demands, travel times, and so on. We can also assume that they are independent from each other, which is not really true, okay? So maybe this is not the best approach what we can do, okay? So can we do it much better without making all those crazy assumptions which are not maybe valid, okay? So a much more data-driven approach. So we will somehow try to use reinforcement learning for that. I'm not really sure how much you are familiar with. I will try to like motivate, explain very easily. So imagine you have a kid. I got two kids, so I know how it works. You have a kid, you buy him this simple low cutting grass machine, and if someone asks him, give him some task, this is your task. I want you to produce this. If you have kids and this is the first time they sit in this machine, clearly you are not a responsible parent, but let's ignore this one, okay? You ask him to achieve this task. What will happen? He will just press some buttons. He has no clue what is the gas button doing. So he just press it. It finishes like this, okay? Of course, you don't give him any reward. You say, no, this was not what I wanted from you. So he will try one more time. Again, given the test and the same task, he will do maybe a little better, but still he will end up like this. Maybe he will repeat like 100 times, 1,000 times, million times. And maybe afterwards, he will achieve the goal like this. So then you give him some reward, okay? Actually, the same is working for reinforcement learning. We can have some kind of like state, which is basically what you observe, basically what's the current state of the environment. So you observe this state ST. The agent, or basically my child, can choose some actions. There are multiple buttons. They can just press or put the steering wheel to the left, or put the gas pedal and so on, or the brake pedal. And basically afterwards, I will observe what will happen. I will get a new state and maybe some reward. I will tell him this was good, you are getting closer to the end goal, or getting somehow bad because you disturbed the machine, okay? So there are multiple rewards. Because now see here, example is for playing this simple Atari game. You can see at the beginning, he didn't know how to play, but after 2 hours of training, he's getting better in playing this game. After 4 hours of playing this game, let's say the AI was playing this game, the reinforcement learning agent will learn how to play it like a professional. You can see he will dig some tunnel here and put the ball on top, and then he will get many points without doing almost anything, okay? You can now see it here. So actually this approach is very powerful. Maybe you heard about this game of Go, where basically DeepMind managed to implement or train this reinforcement learning agent, which could really somehow beat the world champion of the game Go, okay? And actually this was done in 2016, where they use actually many different approaches how to do it, and many different algorithms and different ideas in machine learning. But at the time, they need to have some human knowledge, some human data, somehow like rules and so on to be imposed for this agent. But overall, basically it was pretty good success, but they somehow try to improve this one, multiple papers and so on. And let's say now there's this mu0, which can play all those games, and it doesn't require almost any rules to know, no human knowledge and so on. It can just learn itself. Basically, the question was, can we do the same stuff for, let's say, supply chains, for job shops and so on? So basically, the new approach could be roughly the same beginning. I have this data which I can use to train the agent, okay? I still need to be careful how I build the model, because I cannot just do something simple, because there are some difficulties with the problem which I need to take into account. But once I build a model, I can just use the data to train the model. You will see, I will not assume anything about correlations, about some normality and so on. I can just use this reinforcement learning just to train from the data, and that's it, okay? So basically next time I will do some features, let's say today is morning, or like tomorrow I have some forecast, I can just use the model to give me the solution, okay? So actually this is our approach what we want to take. Okay, so now we'll give the microphone to Ruben, who will speak about the architecture and also the solutions, the results.
Thank you, Martin. So we are going to discuss what's the machine learning architecture we use for that. And the basic block we use was the LSTM network. For solving these problems, we use these sequence models that are well known for working well in language models and speech recognition and other topics. And the main property that this neural network has is that they enable to embed the dynamics of the sequences we are going to deal with. In the case of the vehicle routing problem, could be the cities we visit. In the case of the job shop scheduling problem, are the operations or tasks that every operation has, that every job has. And this is the basic block we are going to use to build our architecture. In the basic how these models work, they have a hidden state in which they are going to embed the hidden information that they are going to collect from the sequence. And there are some gates that are going to enable to enrich this hidden information or to forget features that we are not going to need. So this LSTM network is going to be embedded in our static embeddings for this problem. This is the particular architecture we used in the job shop scheduling problem. On the left of the image, you can see what's the problem definition we used. We use an embedding layer in order to build a latent representation of the predecessor machine and the durations for every specific instance on the problem. And then we use this LSTM network to build the static embeddings on the problem. These embeddings are computed just once and they don't change during the problem. But in our architecture and differently to previous models, previous sequence to sequence models, in our case, we are going to compute for every state an action in order to imitate a constructive heuristic algorithms on these problems. So apart from the static embeddings that embed the information, the definition of the problem, we also need some dynamic embeddings that are going to be changed while the solution is computed on the problem. In this case, it's going to be the machinery state, which is going to be dynamically recomputed for every operation we schedule in the problem. So two parts, one static and one dynamic. And then we are going to use an actor-critic architecture in order to compute the policy that is going to indicate the job that we want to schedule and the value in order to be an advantage actor critic estimator. In order to benchmark our model, we compare this with several heuristics and also metaheuristic algorithms. In the case of heuristics, they are simple local or global dispatching rules that use very few features in order to decide how to construct the solution on the problem. In the case of metaheuristic algorithms, we use just a reference, but we are not directly competing with them because our solutions are computed almost immediately. So they are better compared with dispatching rules rather than metaheuristics. So the first test we did was in very small instances, low-end instances on the job shop scheduling problem. And we did this in order to observe, just learning for a single instance, how better our model works. So we want to find whether our exploration method in the reinforcement learning algorithm is capable of learning a good solution, is powerful enough to explore a good solution. After we verified this, we decided to generalize for all the models, for larger models. And we did this benchmark against tired instances. And in this table, you can observe the quality of the solutions we produce. For several instances on the job shop scheduling, you can observe what is the objective, the gap we left to the optimal, and the time we need to compute the solution, which is almost immediate after the model is learned. And we can observe also that we compare our model against several heuristics, but also a previous paper that was presented in NeurIPS in last year. Even though we show that our model beats the previous NeurIPS paper in all of these instances, we are still far from achieving a competitive model, but we are working on it. At the moment, we achieve very good heuristics, or better than the default ones for low instances, but it is not the case for very large instances. So the solution that was proposed in NeurIPS last year, different to ours, relies in defining the job shop scheduling problem as a fully directed disjunctive graph, in which there are two types of edges on this graph. The first one defines the timing, the time between operations, and the second one defines the operation that need to be scheduled before each other, so defines the order. Particularly, they use a graph isomorphic neural network, a type of GNN that is discriminative in this kind of sparse graphs. And they affirm that this neural network is generalized much better in larger instances. However, they focus a lot on the neural network part, which is needs to be powerful enough to embed rich a policy on the problem. But this is not all. We focus much more in the reinforcement learning part. And even though our neural network is much simpler and smaller, we achieve better results. So for the stochastic version of the job shop scheduling problem, there are some parameters that are random variables. And in our case, we choose the processing time. So as Martin said, the processing time is going to depend on some features. In our case, we choose temperature, humidity, status of the machines. In the classical approach, in order to solve this problem, we built a model based on the features and the historical samples. However, any small change on the results on this prediction means a significant difference in the optimal solution. Therefore, we are going to discuss our error model, which is going to directly learn the solution from the features. In the first we are going to discuss the classical approach. Here, what we tried was learn directly from features using supervised learning on the historical data. And once we have learned or predicted a duration time, we use a traditional method in order to solve the problem. However, as we can observe here, the error is propagated through the processing time, and it's going to degrade our solution. So even though for instances where there is no high variance, the solution might work well. This doesn't preserve the correlation between the operations, and in case of high variance, in our experience, this model doesn't work well. So our approach is the following one. As mentioned, we don't anymore rely on any prediction. The input for our model is going to be the features directly, and we are going to learn a latent space, which is going to embed a latent representation of the duration of the operations that are going to be used as before in order to build the static embeddings, which is going to be combined for every time step with the dynamic recomputation of the embeddings of the machine state in order to compute the actions or the operations that are going to be scheduled. In this case, there is a small difference. In our case, we cannot observe or we don't observe what's the time, the operation time on the machinery, because we don't have access anymore to this information. So we rely on a second a recurrent neural network to embed this information, to embed this logic into our actor-critic architecture. And the results we observe are the following ones. In red, we compare our model against a traditional solver, simplex, that is used after predicting the solutions, the distant matrix. And after that, it computes directly the solutions. The blue line is going to be a baseline. This model is trained with all the information, and we can observe that our models in green and in orange achieve a competitive solution, even though compared with the solver. We also performed some improvements over this model, and the main improvement was incremental learning. In incremental learning, what we observe is that for large instances of the job problem, it's hard to directly explore good solutions. Therefore, we want to facilitate this process. And this is where we apply this incremental learning. In incremental learning, we are going to feed the model incrementally, adding complexity to the neural network. So in the first, we try n-k operations, and we incrementally add the number of operations our model is going to deal with. Therefore, our heuristic, or the heuristic that the neural network is going to embed, is capable of incrementally learning these good policies in easier models and apply them to harder model, which in the end, it doesn't improve the results we previously had, but it accelerates the whole process. In the case of the vehicle routing problem, is going to be the architecture we use is very similar. Also, we use an LSTM network, a recurrent neural network, to embed the features or the feature on the problem, which are the cities, the demands. And based on this information and an attention layer that we applied in order to ponderate the importance of the different cities, we feed an actor critic to compute the actions and to construct the solution. Here we can see a video showing how this model works. So on the right of the image, you can see the attention mechanism that is going to focus on nodes that are going to be scheduled next. And we can also observe that our model doesn't, even though it has capacity to feed more cities, it doesn't play greedily on the actions, but it focuses on long-term rewards and long-term scheduling. So in the case of the stochastic VRP, we build a similar model than the previous one, and we also rely on features because the demands and the travel costs are going to be stochastic. The features we use are the temperature, humidity, and with speed. Also, we present a classical approach on our reinforcement learning approach that is going to learn directly from these features. So, yes. In the case of the stochastic VRP, the model is similar to the previous one, so we don't discuss. But we discuss the benchmark. We compare this model using tabu search, specifically for the stochastic vehicle routing problem and the coarse entropy method. And we observe that the solutions that we achieve are competitive against these benchmarks. But we have an advance when we compare to these meta heuristics. And it is that once the model is learned, we don't recompute it. We directly compute a solution, and the inference solution is not comparable with these meta heuristics. So, yes, that's all. So, thank you.
Thank you, Martin and Ruben. Are there questions? Yep, hold on 1 second. Here we go.
Can you mention the training data set, the features, the why? In particular, you didn't mention, is there real data or you simulated the data?
No, we use simulated data for the stochastic part, and we build our stochastic model, and we define our features. Yes. So it's not real data; it's our model.
I see. For the LSTM, and what is the loss function do you use?
Mean square error, I believe. Yes.
Is it a robust, or have you checked other loss function type?
Yes, we did, but it's a de facto. So yes, yes, we didn't, or in my case, I didn't pay attention on this fact. Yes.
Okay, thank you.
Thank you. Any other questions? All right. Then thank you both again.